you hear me okay? Awesome. Well, thank you all for being here. It's so nice to see so many familiar and some unfamiliar faces. So I'm going to tell you a little bit about the research I do, but also a little bit about how I like to think about things and what got me interested in this field to begin with. And so the title is, 10 trillion degrees, which seems like an unfathomably large temperature. And what does it tell us about the earliest universe? So I'll start with this picture here. This is going to be an interactive talk. So what is this? These are not nuclei. There's no nuclear physics here. What is this a picture video of? Yeah, what kind of birds? Excellent, excellent. And what's amazing is, this kind of coordination is what we call an emergent phenomena. That means there's no new law of physics here, right? It's existing laws of physics that somehow leads to this surprisingly coherent pattern, some kind of collectivity. And you can say, what's the underlying origin? How does this work? And I kind of like the theory that there's an alpha bird, and it's conducting, and all the other birds are following, like the students in my class, right? They're all sitting down here, yeah? But in fact, it turns out that scientists, not me, discovered the way these patterns emerge is that it's all short-range interactions. Each bird just looks at the 3 or 4 birds right around it. That's all they look at. And the next bird over looks at the 3 or 4 birds around it, and this kind of pattern emerges, even though nobody looks a long ways away to see what some other bird is doing. That's kind of fascinating. It's not obvious just from watching the video. How does this work? This takes a second to start. There we go. This is the average temperature, month by month, spiraling around year by year. So for a number of years, I've taught the energy and environment class here. And it's a great class because I learn stuff every year. And how does this work? Well, it's greenhouse gases. And the most important thing to me is when I think about ice ages, you think, well, the Earth moves in its orbit a little bit away from the sun. It gets colder. But if you calculate how much colder, it's tiny. And that tells us it's all feedback mechanisms. It's all ice melting, absorbing more of the sun's radiation. And I think it's timely. Whoops, if I can use my pointer. Maybe it's being blocked. Or maybe I'm stuck. All right, I'll use my, just very slow. All right. The scientific method is something we really need to respect. The data on that graph may look kind of colorful. It's data from NASA. It's important we keep collecting that data and paying attention to it. One more. There we go. So a number of years ago, I got interested after going to a talk kind of like this one about the idea of how do cloning organisms evolve. And actually, Craig Fogel, who is the first author on this paper in genetics, was an undergraduate student working with me. And we were trying to answer the question in these simple cloning organisms, what wins out? Is it lots of little tiny beneficial mutations, or is it really big jumps? And we were able to mathematically solve that problem. Craig went on to get his PhD in physics and is now vice president at Citigroup. So maybe he'll have some influence there. Okay, so this is what I really have been focused on for a long time, and that's what this talk is going to be about. It's about the quark gluon plasma. So it's this fancy computer simulation, and by the end of the talk, I hope you have some idea what those lines and colors mean. That's my goal. So I've been doing this for a long time, and I don't know if Mike Dubson is here. He might be busy, but he told me that my web page is out of date, so it still has this picture on it. And so I took the other picture there. So I've been doing this for a long time, so I'd like to think I could explain some of this. I will say it has meant not focusing as much on other things. So these are the same shoes. So I have one pair of shoes, about 25 years. I think they'll go another 25. So that's the thing about physicists. You got to focus on some things and maybe a little less on others. All right, so I thought about this a lot in thinking about this talk in terms of, what are people going to get out of it? So I like this in Stephen Hawking's book. His editor told him that for every equation he included in the book, it would cut the sales in half. People do not like equations, which is really a shame. I like equations. My students, they like equations, yeah. So he only included one equation, and that was E equals mc squared, right? We can convert energy into matter, or we can also convert matter into other forms of energy. I'm going to have a couple of equations, but you're not throwing dollars at me at the end, so you can't really have you can walk out, but they don't serve the food until we're done, so you can't like go out there and snack away, you runners back there. Yeah. All right. So everyone knows the Big Bang Theory. I'm not a big, huge fan, but I'm going to show you this little video clip, and hopefully it'll work. This is the simplest possible explanation of the quark-gluon plasma.
It's a quark-gluon plasma. No. It's asymptotically free partons inside a quark-gluon plasma. Nothing but quarks. It's an observational rebuttal of the lambda CDM model of the universe. No. It's a chocolate chip cookie! You missed that. Hey, if you want someone to guess chocolate chip cookie, you draw a glass of milk next to it.
So that's my simplest explanation of the quark-gluon plasma. So the way I'm going to start is, probably many of you know this, but the Greek word atomos, right? It means indivisible or uncuttable. And that's the origin of the English word atom. And actually, I'm very disappointed that Alistair Norquist, who's a professor of philosophy, isn't here, because I actually found this interesting in reading a little about this. What really bothered people about the idea of atoms was the idea that there was empty space or void in between them. And so they claimed that what is not exists, these voids. So I don't understand philosophy, but I'll have to ask Alistair a little bit of detail there. So you could break things, right? And it doesn't take that much energy. You just need a guitar. If you want to break molecules, you can break them up by burning something, right? That has enough energy or temperature to break molecular bonds. If you wanted to break atoms, you could use like an arc torch that has a high enough temperature. You're going to break atoms. You're going to ionize them. If you want to break up the nucleus, right, you might need something like a nuclear bomb. The energy scale between breaking molecules with a flame and breaking up the nucleus might be about a factor of 1,000,000 difference in energy. What about one step down? Inside the nucleus, there are protons and neutrons. And you could ask, can we break up the proton? Is that even possible? So is it breakable or unbreakable? So here's a very simple atom, hydrogen, with a proton in the middle and an electron in orbit. And the atom can be easily broken apart. But the electron is a fundamental object having no discernible size. And so even Chewbacca cannot break the electron into pieces. There are no more pieces to break it into. But the proton is different. It's not a fundamental particle, and it's made up of other particles called quarks. So it does beg the question, could we break it into those pieces and study those quarks? Well, where do these quarks sit? So the quarks have funny names like up, down, strange, charm, top, and bottom, because even physicists like to be a little bit clever at times. And so the proton is made of 2 up quarks and 1 down quark, and the neutron is made of 2 down quarks and 1 up quark. And then there are interesting particles like antiprotons that are made of antiquarks, which makes total sense. And there are strange particles that have strange quarks in them, like the lambda particle. And so these protons are made up of these more fundamental particles called quarks. And the quark discovery, both on the theory side and experiment, were both awarded Nobel Prizes. One for the theory work back in 1969, and for the experimental confirmation in 1990. And so those quarks, in fact, are unbreakable. So what does a quark look like? They get it, yeah. So this is our dog, Quark, which my children named, so it's not my fault, right? But what does a quark really look like? Okay, so this is Quark disguised as a pickle. That's not what quarks really look like either. So quark doesn't really look like anything. It has no discernible size. It's a point-like object that we can't really directly see. So no one has actually ever seen a free quark by itself. These quarks are trapped by the nuclear force inside of objects like protons. And that brings us to our other kind of particle, and those are called gluons. So here is a simulation of 3 quarks. Those are the colored objects. And they're held together by the interactions, by sort of tossing back and forth these other particles called gluons. And those gluons are like springs. And if you go to the gym and you grab some big, spring and you try to pull it apart, it gets harder and harder as you pull more and more. And actually, with these quarks, it would be these gluons fight back more and more. So it's actually impossible to pull a quark all the way out. It would take an infinite amount of energy, more energy than in the entire universe. So I thought this was very clever. There's a soil stabilizer called gluon. I had no idea. And for this soil stabilizer, they awarded the Nobel Prize. No, they did not do that. But this idea of confinement, of trapping of the quarks inside the proton and neutron and nuclei, right, won the Nobel Prize in 2004. And I have no idea about this product. So it would take an infinite energy to pull a single quark out of the proton. But what if we try something a little clever and don't do that? Maybe instead we can melt these protons. So instead of pulling one quark out, maybe we can melt a whole bunch of protons and form a plasma of quarks and gluons. So that's what that chocolate chip cookie drawing was earlier, right? That's this idea of a quark-gluon plasma. So here's a $25 Bunsen burner. You could go down to the store and buy it and start heating up something in your house, right? And see, well, when do I melt the proton? And the problem is that we need a temperature of 10 trillion degrees. So that's about 100,000 times hotter than the center of the sun. So that's pretty hot. So even in the center of our sun, there are protons and neutrons with quarks and gluons trapped inside of them. They are not free even in the center of the sun. So thought I'd think a little bit about hot and cold, so I thought I would do this as a quiz. You can all reward yourself with a snack if you get it right. What is the hottest temperature ever recorded in Colorado? Any guesses? 115. Damn. All right. You don't answer the next one. That's, yeah, okay. Someone else, someone from this side of the room. What is the coldest temperature ever recorded in Colorado? 1985. Negative 40. Minus 70. Yeah, that's pretty close. Minus 61. So all of you who were complaining about the weather a couple weeks ago, come on. Actually, I did hear this thing. If it was below minus 40 Fahrenheit, for more than, it's something like 40 hours, it would kill all the bark beetles inside the trees. And so people were hoping for, you do get below -40, but not usually for that long. But that would get rid of the bark beetle. So okay, those are local temperatures. Now we'll talk about some other local temperatures. So Carl Wyman and Eric Cornell, two of the physicists here at CU, shared the Nobel Prize in 2001. They created what was called a Bose-Einstein condensate. Oh, now I realize I'm standing in front of part of the screen. And they achieved a temperature of -459.67 degrees, so almost absolute zero. And at the time, that was the coldest temperature ever recorded in the laboratory for any matter. And we're at the opposite end of the scale. So Professor Dennis Parapolitz over there, and I saw Ed Kinney come in. He's way back there. Hey, Ed. We're a part of a team that back in 2010 created the highest temperature matter at 7.2 trillion Kelvin. We did not win the Nobel Prize, but I did once find a buffalo nickel. So I feel, for those of you old enough to know what that is, that's pretty special. It's like the Nobel Prize and then like finding the nickel. It's like right there. All right. I promised something about the universe. So as you go back in the history of the universe after the Big Bang started out very, very hot. All the energy in the universe is in some very small volume. And as it expands, it cools off, right? And so when was the universe hot enough to be 10 trillion degrees? Well, it's really, in this stage here, it's a few microseconds. So 1/1,000,000th of a second after the Big Bang, the entire universe was a quark gluon plasma. And then it expanded and cooled off. And once it cooled off below something like a few trillion degrees, then the quarks and gluons were trapped back inside protons and neutrons and nuclei all the way until today. And the universe continued to evolve that way. Eventually, the protons and neutrons cooled off enough to form nuclei. Eventually, things cooled off enough to form atoms. And from there, we end up getting all of our stellar evolution, et cetera. So my field, and what I'm interested in, is very first few millionths of a second in the beginning of the universe. And something very interesting happened back in the 1970s when people started thinking about the idea of quarks, and not my dog, they weren't thinking about her yet. But what about in the laboratory? So what if we could accelerate large nuclei like gold up to very near the speed of light? So like 99.9997, the speed of light, and collide them. By E equals mc squared, there's my first equation, all that kinetic energy can get converted into creating new particles at very, very high temperatures. And that's the experiment that we wanted to do, right? Could we accelerate these large nuclei up to very, very high speeds and create a very tiny droplet of this quark gluon plasma that was the matter of the earliest universe? So can we make this work? And it wasn't obvious whether it would work or not. And so the first real accelerator to do these studies was at Brookhaven National Laboratory at high energy, and that's out on Long Island in New York State. And there's another facility that I'm not going to talk about as much today. That's the Large Hadron Collider. That's on the border of Switzerland and France. And that's also where the Higgs particle was discovered. But 1 month a year, we use that facility to collide large nuclei to study the quark gluon plasma. And these are a set of the different experiments that are looking to understand the plasma properties. So these are our laboratory Bunsen burners in some sense. And they cost more than $25. To give a little bit of a scale, when the machine up at the top there at Brookhaven National Laboratory was built back in 1999, it was about $1 billion. It was a $1 billion project. And I think there's been some inflation since then, so a little more expensive. OK, so this is a picture of Long Island. How many people have been to Long Island? Yeah, it's OK. It's OK, you know. It's okay. So that little circle in the satellite view is the circle that's blown up there. That's the accelerator ring. So instead of burying it deep underground, right, to prevent radiation exposure, it is, oh, am I lost? Yeah, we're good, okay. It's built underneath what's called a berm. So it's like a hill that goes over the accelerator, so you can really see it. This is a picture. So actually, this is not the accelerator. This is the National Synchrotron Light Source. That's another billion-dollar project. Smaller, less interesting. Sorry. But the ring is up there at the top. The ring is up there at the top. And the really, really awesome apartments on site are over here. I'll show you that. So as many of you know, I am a social media maven. Is maven the right word? So I have at least 12 followers on Strava. At least. And so my pastime while there is running. So you can run about 2.5 miles around the inside of the accelerator ring on the road. And if you're adventurous, you can run on the trail that goes around the outside. And the Brookhaven National Laboratory is many, many square miles. And back before World War II, it was a training ground. So there are all these trails through the woods and stuff that used to be part of basic training. And yeah, there's a big contest, too. You could find the most box turtles. So Brookhaven is an interesting place. That's like a statement, just in general. So for those of you who may not be familiar, so back in 1961, Brookhaven hosted the Gamma Forest. They just put this huge radioactive source out in the middle of the woods to see what would happen. And they basically figured here, everything within about 30 meters would be killed and on out. So when you hear these things like, it's the bees and the cockroaches that are going to survive nuclear war, that's what they were doing out in the woods. And it's somewhere along one of these running routes, like off that way. But Brookhaven's an interesting place. That's the main thing. So for 10 months, I was the run coordinator this last year, so I got to act like a graduate student again, which is wonderful. That's the best time of your life. This is my very humble abode, and there are millions of turkeys, and I don't know what baby turkeys are called, turkeylets, something like that, all over the lab. And there are all these jokes about them being exposed to radiation, but I counted, and they all have 2 eyes. So I think that's probably, we didn't eat any of them. That's not allowed. All right. So, here's a graph and equation number 2. Paul will like this equation now. Okay, so when we collide these 2 nuclei at very, very high speed, sometimes they don't hit exactly head on. They kind of are edge on a little bit. And all of the energy gets deposited in sort of this ellipse, this almond shape. And the neat thing about that is, if you simulate, on a computer simulation, what happens, the quark-gluon plasma expands out to the sides more. It's kind of pushed out along the sidewards direction. And we only have one variable. You don't really need to know it. But this V2 characterizes how much it pushes out to the side. And that's a very important measurement that we try to make. So when that simulation is done running at the end, all these little cells are little cells of a fluid, and the arrows are how fast the quark-gluon plasma is moving. And the longest arrows are at about half the speed of light. So this collision happens, we create tens of thousands of quarks and gluons in this little fireball, and it explodes. And we're measuring the byproducts that are speeding out towards our detector at about half the speed of light. And way back about 20 years ago, we were part of the Phoenix experiment and made this plot. And all you need to know is that it's this push to the side as a function of the momentum of the particles. And all the lines kind of go pretty through the points. And what was interesting was that this was a model of the plasma flowing as a fluid with no friction at all. No what's called viscosity. That's what we call a perfect fluid. So if you've ever heard of a superfluid before, that's a nearly perfect fluid. And that cell in the middle there, that's at about 2 trillion Kelvin, sort of at the end of the evolution. At the beginning, those red color cells were more like 10 trillion Kelvin. So, but what about viscosity? So honey is a good example of something that's very viscous. It means it has internal friction. When one part of the honey wants to move, it drags the other along with it. And it turned out that relativistic viscous hydrodynamics was one of the major unsolved problems back in 2007. And Paul and his wife solved that problem. So it's an extremely famous paper. I think it has almost 1,000 citations or something for solving this problem. And that allowed us to measure just how perfect a fluid, just how easily did this quark-gluon plasma flow. And so this is a more sophisticated simulation using computer code from Paul. And not only can you measure push to the side, you can measure sort of spatial moments that are triangular or quadrangular or pentangular. And you can compare them to the measurements we made. And that agreement between the theoretical modeling and the experimental data we took basically told us that the quark-gluon plasma is actually the most perfect fluid ever created. And so that's what that early universe is like. In fact, the quark-gluon plasma is more perfect than what you sometimes hear about with superfluids. And this is just a picture of our universe and the fluctuations in temperature when you look up in the sky. These are simulations, each one of these nuclear collisions, and the temperature fluctuations at the beginning. So each collision is like a mini universe that's exploding outwards towards our detector, and we study billions of these to get a big statistic sample to be able to understand what's really going on. After that, we had a very interesting idea, and that was, can we engineer the shape of these little droplets of early universe matter? And the way we would do this is, instead of colliding two big nuclei like gold, we would collide a proton on gold. A deuteron has one neutron and one proton, so you get 2 hot spots. Helium-3 would make 3 hot spots. So what you would expect is that this would have the largest V2, the push out to the side. This would have the largest V3 in 3 directions. And this artwork was done by Javier. Hi, Javier. And was on the cover of Nature Physics, which was very exciting back at the time. And again, you don't have to read too much into the graph, but our group actually published a paper together with Paul and others predicting what would happen for these different shapes. And then we went and measured it, and the agreement was really quite good. So it's a hypothesis confirmed by experiment. We really can manipulate the shape of these little droplets of early universe matter. And we even made it to the Department of Energy website, which I'm sure has been scrubbed by now. But this is a great picture. I know Jerry's probably happy to see the old Phoenix experiment there. Yeah. All right. Like all physicists, you never stop, you never retire. I guess my wife says I can't retire yet. Yeah, I don't know. Yeah. Okay. So we said we'd build something new. What do you want to do next? And so we proposed building the S-Phoenix experiment. To give a sense of scale, this is Chewbacca. And I suspect if I ask how tall Chewbacca was, you're going to know the answer. Because you're kind of on. How tall was Chewbacca? 7'4". Ooh. I think it's like 9. No, go look it up. Look it up. Fact check me. I'm okay with being fact-checked. Yeah. And there are probably some lawyers in the audience. I won't make too many lawyer jokes, but I'm the one who put the Superman logo in Super Phoenix. And then the government's like, oh, we're going to be sued by DC Comics. And I tried to explain to them that, like, if it were Marvel, they would sue us. But DC Comics, they're in such disarray, they would never figure it out. But they stopped showing it. But I still show it because I only have that nickel to give them if they want to sue me. So to give a little idea, it takes some time. We proposed this back in 2010, and we built a big team of people. So here are some colorful pictures. This is a picture from during the dark ages of COVID. Here are some of my students who drove all the way across the country to help build part of the detector, wearing their masks all the time. The research is funded by the US Department of Energy. We also get money from the National Science Foundation. I've also gotten very good support here at home from the University of Colorado and some other places on my nice sabbaticals. There are so many people, but I want to give a couple extra shout outs. Dennis and Ed and Paul and many more who are here have been great faculty colleagues. So many people in the group. I see Sherry back there. Maybe she hasn't left yet. Malia, Robin, Alex in the building, Mike, in the team. It's a big effort. It takes a big team to make it all happen. So it's very fun to build something new. This is a bar in Tennessee, and I'm no longer quite clear where. It's near Oak Ridge National Laboratory. And in that bar, my Russian colleague, Edward Kistinev, drew this up on his napkin. And that was the design for what's called the hadronic calorimeter of our detector. So we really started out back in 2010. We would have every month a workshop somewhere else in the country, and we'd get together, and we would go to bars and draw napkins. And eventually, it led to something. So actually, here in our lab over in Duane, we don't do the nuclear reaction at 10 trillion degrees, right? That's at Brookhaven or in Europe. But this is actually a fiber inside what's called a scintillator. And we went away from his great idea of this snake pattern because it was too complicated on the napkin. And this is part of the detector coming together. There's a superconducting magnet that you could basically, probably if you were Chewbacca, you could just stand inside of it. These are all the different detectors coming together just in the last couple of years. It really took a decade to go from the napkin to the real thing. This is a picture inside the bore of the detector. So the explosion is occurring in the middle, and we're measuring everything that's coming out. The specialty in our group is high-speed digital electronics. So these collisions are occurring every 1/10,000,000th of a second, and we can't record all of that data. So we have to very, very quickly decide, is this an interesting new universe or not, and decide whether to record things. And all the fiber optics coming in are bringing in all those signals, and these are my graduate students. And let's see, it's very slow in the animation. So there's Dan, who's over there, and my really wonderful friend and colleague, Chen-Yi Chi, who's at Columbia University, who I've worked with for 25 years. That was at a retirement party this last summer for one of the technicians there who helped us put all of this together. So we're back sort of towards the beginning. How does this work? So this background image is this quark gluon plasma flowing like a fluid. Every once in a while, two quarks will interact with a lot of energy and shoot out to the sides in sprays of particles. And that's what the S-Phoenix experiment is looking for, right? That's what we built this to measure. And after 10 months of not getting a lot of sleep out at Brookhaven and watching the turkeys and trying to find the radiation forest, we've made some of our first measurements. And these are energy distributions from our different detectors. And this is an event where we really have these two quarks shooting out to the side. Now, that in and of itself is not new, but now we're seeing how these quarks go through the plasma itself. And that's going to teach us a lot about what those plasma properties are. Oh, and I'm pretty good on time. Wow, I could have told more jokes. Okay, real experimental data. So analyzing the data right now, well, they're all sitting over there, so they're not analyzing it right now. But as soon as this talk is over, they're going to skip the food, and they're going to go right back to the lab. Maybe. We'll see, yeah. All right, so there are really amazing discoveries to come. But I do have to say, science and scientists of all backgrounds are really under attack. And it's sad. And I think the message is we should not go silently, right? We've got to stand up for the scientific method. We've got to stand up for fact-checking. Did you fact-check me? How tall is Chewbacca?
It's 7'6" is including the costume, and 7'3" without the costume.
With the hair, brushed up? Yeah. Because my son is shorter than me, but with the curly hair, he's as tall as me. I'm gonna recheck this, but I think that yeah, it's I think these are things we have to stand up for. So, sort of summary, we've really in our field, it's not just me, it's a big team effort, have discovered the quark-gluon plasma as really the most perfect fluid of any material we know of, and it's maybe more than the discovery, what's really pleasing to me is to work with so many smart, dedicated people over the year and see them succeed in doing all kinds of things. And we really have exciting new data from S-Phoenix that we've just taken, and it's really exciting to try to, after 15 years from the napkin, to see what the answers really are. And so I really appreciate all of your support in coming, and my leaving message is to stay curious. Thank you.